Hello everyone, my name is Marc-André. I'm a fourth year PhD student at the University Mainz in Germany, and today I talk about Gecko FS, a temporary burst buffer file system for HPC applications. Gecko FS is a joint work between the Barcelona Supercomputing Center and the University of Mainz, and we have been jointly working together on the files for the past year and a half. In this talk, I will talk about the motivation, the design considerations, its use cases, performance, and finally discuss what we have in store for the future. Now, in today's HPC systems, there are more and more data-driven science applications as well. And these applications, for example, have new requirements for the HPC file system. So in the past, when applications would use parallel file system like Lastro and GekkoFS, the accesses would be mostly sequential. But with these newer applications, they also have now to deal with many metadata operations, random access, or small I/O requests. There have already been a couple of solutions that try to deal with that, so that these new access patterns are somewhat aligned to the capabilities of the underlying file system. This can be, on the one hand, done in software, for example, Adios, where the software is adapted to this new layer. But unfortunately, if a new API is used, for example, then this is typically very time-consuming to change the application for that. Is often difficult to couple with big data and machine learning libraries, and sometimes, depending on the algorithms that are used, not possible. The other solutions are hardware solutions, where, for example, a bunch of SSDs are put into a box, and then they are used as a layer as well, so that, for example, random I/O is done on these SSDs, and then finally they will be written out to the parallel file system in a more sequential fashion. Now, of course, such a hardware solution is very expensive because you have to buy the hardware. And another approach is where Gecko FS is coming from, is burst buffer file systems. And burst buffer file systems make use of a new development in clusters where now node local storage is also available at the compute nodes. And this is typically in the form of SSDs. Normally these are just plain SATA SSDs, but in the future, depending on the prices and if it's affordable, there will also be NVMe SSDs. And the idea of a burst buffer file system is that you would pool together all of this storage on the nodes that are otherwise unused and use them as storage for the applications. Because actually this development is so new that many applications are not making use of that local storage because it's just local and not shared, available in a shared fashion. These file systems already exist. There are software like BGFS Beyond, which can create such a file system in an ad hoc fashion, but they're often full on POSIX compliant, and they're facing certain difficulties when scaling to a large number of nodes. Now, the goal of GekkoFS in the beginning was to have a very lightweight file system that can be used by anyone. So it doesn't involve an HPC administrator, and that it can just run in user space during the lifetime of an HPC job, which can just be used by the user that is running the job. The file system should then use all the node local storage, whatever is available. It could also be a RAM disk or SSD. And then all the input data that the application needs is staged in before the job really starts, and the output data is staged out and moved out to the parallel file system after the job finished. But with GekkoFS, we really wanted to focus on making metadata more scalable, which has been a problem in general for many file systems, that there are bottlenecks when having, for example, a lot of metadata operations if, for example, a lot of file creates are done in the same directory. Further, we have looked at studies to see what functions are actually used by applications in HPC systems. And usually what we found out that operations like a rename operation is not really used by applications themselves, but rather done by the user later on the command line to see if something changed. And similar things we have seen for operation like readdir that is caused by an ls operation that is usually not used by an application. So we want to focus with GekkoFS on functions that are actually used by applications and optimize for that. Of course, we have a couple of assumptions here. Because we are eventually consistent, is that each of a file system object is accessed by a single application at a time, and all the complete data set must fit into the node local storage of all nodes. Otherwise, this doesn't work. So how would that look like? So here we have 6 nodes that are used by 2 applications. Each of them is using 3 nodes, and they're having these SATA SSDs available on each node. And the ad hoc file system will then pool together the SSDs to one file system that the application can use doing the job. And later, when the application is finished, it'll move the data out to the parallel file system again. So in addition of having potentially a better performance depending on the environment with an ad hoc file system, because the application is using that file system without any interference, you can make the case that also because applications that have a bad I/O pattern where the I/O operations are all over the place, they're taken away from the parallel file system so that they don't interrupt other users as well. Because after all, the parallel file system is a shared resource, and if it only has to deal with very efficient I/O patterns, such as sequential I/O, then it works a lot better. And the idea is with an ad hoc file system like GekkoFS to absorb these I/O patterns so that we can later write them out in a more sequential fashion in the stage out process. So how would that interference look like in the real world? So for that, we looked at the throughput variability of GekkoFS at Mare Nostrum 4 at the Barcelona Supercomputing Center. And what we have seen is that depending on the time of day and what day we have run some performance benchmarks, that we got a big difference in I/O throughput, both in terms of read and write, but for write it was even worse. So that is what you can see here. On the y-axis you have the performance, and the red dots here are, each of the dot is a different performance test, and it changes over orders of magnitude depending on the day. And this is of course expected because one user is not using GekkoFS in an isolated way. So there will be some interference if other users are using GekkoFS as well in whatever fashion. GekkoFS, on the other hand, has very stable performance because the users are using that file system without anyone interfering. So there's low or even zero cross-application interference there. If this plot here is mapped to the worst case performance, you would see even more clearly that the more nodes are used to write, for example, the worst case performance that you can experience on GekkoFS actually goes down, while GekkoFS is scaling up the more nodes you're using. And eventually, the more nodes you use, you might even be faster than the parallel file system, depending on the environment that you're in. So the key points here for GekkoFS are that there is less interference with the parallel file system and other applications because they run on their own. It runs completely in user space, so there is no kernel extension needed. GekkoFS, because only one application is using it at a time, we can also tune it for a specific application. in terms if it's using a lot of big I/O or a lot of smaller I/O requests. We can specifically tune Gecko FS for that. This cannot be done with a parallel file system because they have a use case that the file system must work with all applications reasonably well. In general, GekkoFS works with any backend. It doesn't matter if it's an SSD, an NVMe, or a RAM disk. As long as it has a path that is available to the user, we can use that. For the future, we also work on having support for persistent memory, but for that, the implementation, of course, looks a little bit different. But we will have that in the future as well. But ultimately, the performance of the file system depends on what network is available, if we can use OmniPath, InfiniBand, or remote direct memory access to move data around. So now I want to go more into detail about our design considerations. So when we first designed Gecko FS, we looked into other file systems that provide a strong consistency, and it was very clear that it has a number of disadvantages when strong consistency needs to be guaranteed. This is because usually then storage nodes need to coordinate each other in some form of way, which can cause operations to be delayed and ultimately then causing scalability issues. So when we relax file system consistency, we can simplify file system protocols and also have no central component and therefore no internode locking mechanisms that would slow down the file system. So for that, GekkoFS is loosely coupled. No server or client is communicating with each other, only clients to servers. And each client can decide on its own to which server a request is sent. And then the server can independently deal with that operation without talking to other servers or clients. Also, what that means is that we can depart from a hierarchical namespace and provide a flat namespace, which in addition helps us providing scalability. So as you can see, we focused a lot on metadata when we were designing the file system. And for that, we also looked into how metadata handling is done internally in parallel file systems. And it's quite apparent that, for example, directory blocks or indirect blocks in inode, they are not designed for parallel access because they were initially introduced when there were only local file systems, and providing strong consistency on these data structures leads to a lot of heavy communication between nodes, intricate locking mechanisms, and after all, high code complexity. And then what we can see in the common parallel file system is poor scalability if, for example, a lot of metadata operations are happening at the same time in a single directory. So instead, for GekkoFS, we first decided to remove most metadata that are potentially not relevant. For example, timestamps and permissions might not be relevant for a temporary file system. Although in our case, these are actually also configurable. So if they're really needed, they can be turned back on, but by default, they are turned off. So that means that there are less metadata updates in general, and that there's also less space used. Also, what I also talked about on last slide is that we can compute the metadata destinations on the fly and then let the target node handle the request independently. And this also works for data as well. And I will talk about that later, how data actually works. So if we now look at the big picture, GekkoFS consists of two parts. The first part is the GekkoFS daemon or server, which is using a RocksDB key value store for storing metadata and the node local file system to store data. The second part is the GekkoFS interception library or client that communicates with the servers via the Mercury RPC framework. And it is using the system call intercept library from Intel to intercept system calls. So we're using syscall intercept so that we don't need to recode the whole libc library when we would use the normal LD preload technique. But even with the syscall intercept, the application still only uses LD preload, and then we can intercept the functions that is invoked by the application, and if the path is going to the GekkoFS file system, we will act on that accordingly. So in addition, the library also has a file map module, which basically only deals with the file descriptors that would normally be handled by the kernel. But since we're only sitting in user space, we have to do that in user space as well. So with regards to how data is handled in GekkoFS, I have a 3-node write example here. So on the right side, these nodes here are the GekkoFS daemons on another node, for example, and here on the left side you have the GekkoFS library. So in this case, the application is issuing a write system call, and then the library will chunk up that write buffer into equally sized chunks, which are configurable in the file system, and then computes the destination for each chunk independently. So we're doing that by simply using the file path and the chunk ID, hash that, and then determine to which node it would go. And in this case, chunk 0 and 3 would go to the same node. So it packages these two chunks together, sends an RPC to the daemon of node 1, which will then transfer the data to itself and then write it down to the node local file system. So as you can see, the number of daemons that are part of a given IO operation depends on the chunk size, but also on how big the IO buffer is. So if the IO buffer would be so small that it fits into a single chunk, then there would only be one chunk, and therefore only one daemon would be part of that operation. So you could already see how a configuration of the chunk size could change for your application how much the data is distributed. So changing the chunk size is one of the configurations that we have to tune the file system into your applications, but you also have several other configurations available, such as changing the data distribution or how a directory is handled within the file system. So how would you use GekkoFS? First off, you would start the servers with the GekkoFS daemon library. Then you define where the data would be put. This would be the local file system. Then where the mount point, the virtual mount point of GekkoFS would lie. And then a host file path that should be put somewhere on a shared path that is accessible by all clients. And basically we use this host file so that servers will register themselves to that file. So then later you would use an environment variable, libgeckofs host file, that points to that host file so that the client would know where to look up that file and that it knows which daemons are part of that file system. So for starting the daemons, we have a corresponding script that could help you start all of them up on a number of nodes, but you can also use MPI or srun to start the daemons on whatever number of nodes you want. To then use GekkoFS in your application or with a normal shell command in this case, what you would do is simply using the LD preload environment variable and point it to the intercept library of GekkoFS. And then you would simply use, in this case, copy from some real path that is accessible to the GekkoFS mounting path and then put it there. So and if you then call LD preload again with a cat, for example, and want to print the data on the shell, then you can just do that. And this is simply how you would use GekkoFS. We have a number of use cases already where GekkoFS is used. So one of the most widely known is perhaps OpenFOAM, which is a computational fluid dynamic solver. And this is used not only in Barcelona and University of Mainz, but also in others. But specifically in Mainz and Barcelona, it solves metadata issues of the parallel file system. There are other use cases for bioinformatics, which sometimes tend to create a lot of small files, but also physics, where we would look at how we can use a longer term GekkoFS as a campaign. So for example, some simulation have several steps that are stretched over multiple jobs. So it would make sense to write the intermediate data of these steps not back into the parallel file system, but keep it in the burst buffer file system for a longer period of time. Another idea would be that if jobs using the same input data at the same time, and it is a larger amount of data that is used as input, it can stay at a burst buffer file system somewhere in the cluster so that the parallel file system is not disturbed all the time. In addition, we also use GekkoFS for research, in this case as a framework to understand the application behavior, not only how the I/O behaves in terms if it's only sequential or random, but also what functions are used, and what configuration we could introduce that could help an application, and ultimately the file system to be faster. In addition, we have a collaboration with the University of Rio Grande do Sul in Brazil, where an I/O forwarding layer is implemented into GekkoFS. So next I want to talk about some results. At Supercomputing last year, we submitted to the IO 500 10-node challenge and placed fourth, which we were very, very happy about. These experiments were run on the next-gen IO prototype, which uses DC persistent memory and 2 omnipath adapters per node. There is a new submission deadline next month where we will also submit, and we hope that we will get a much higher score there. So yeah, keep an eye out on this one. In terms of general performance results, we ran some benchmarks on the Mogan 2 supercomputer at the University Mainz, which uses a 100 gigabit omnipath. And in this case, we want to show you how fast GekkoFS can go, how many metadata operations can be done per second, and how the data throughput looks like and how it scales with the number of nodes. Mogan 2 uses or has SATA SSDs available at the compute nodes, which we use to store metadata and data. All operations are synchronous and there's no GekkoFS caching involved. So first off, we look at metadata performance. For that, we compared GekkoFS to BGFS and weakly scaled 100,000 files per process to up to 512 nodes, whereas each node is using 16 processes. So at 512 nodes, more than 800 million files are within the file system. In addition, we compare for BGFS the single directory and the unique directory case. In the single directory case, all files are put into the same directory, where in the unique case, each process is using its own directory. And the rationale behind this is that in many file systems, metadata performance is higher if each process is operating on its own directory. For GekkoFS, it does conceptually no difference if we use a single directory or a unique directory, because we are working on a flat namespace and the performance in both cases is the same. Now, if we first look at the create performance, here on the y-axis, measured in operations per second on a logarithmic scale, we see that GekkoFS and BGFS, in the case of the unique dir, are scaling linearly with the number of nodes. In the single dir case, BGFS stagnates already at 4 nodes because only a single metadata server is used in that case, so it's not utilizing all of the metadata nodes that are available. At 512 nodes, GekkoFS reaches up to 46 million creates and has a over 6 times higher throughput than in the BGFS case. For stat operations, GekkoFS and BGFS in the unique case are very similar, but we see the same behavior if BGFS is operating on a single directory. For the remove case, GekkoFS is again scaling linearly with the number of nodes, but BGFS in this case also stagnates at 8 nodes at the unique dir case. If we look at the I/O performance of GekkoFS, I present here the sequential I/O throughput in a file per process case. In this case, 4 GB per process is written and read. We also differentiate between different I/O sizes, starting with 8 KB per write up to 64 MB per write. And in addition, each bar has the theoretical accumulated SSD performance if we would combine the performance of all nodes together. This way we can see how much throughput is lost just because we are working in a distributed way. On the y-axis, we have the megabytes per second, again on a logarithmic scale. And as we can see, similar to metadata performance, GekkoFS scales linearly with the number of nodes, or almost linearly with the number of nodes. But larger I/O sizes work better because, as we have seen earlier with the I/O workflow, if a larger I/O size is used, then more daemons will take part on each I/O operation. In this case, to give you a number here, for 512 nodes, we have 140 gigabytes per second in write speed, which is about 80% of the bandwidth that we get through the SSDs that we have. And for read, we have around 200 gigabytes per second, which is about 70% of the bandwidth available through the SSDs. Now we've compared this again to BGFS. We compare here only the 8 kilobyte case and the 64 megabyte case to see how both file systems behave with these different I/O sizes. And what we can see is that BGFS Beyond is also scaling linearly, but BGFS tends to perform better when smaller transfers, when small I/O sizes are used, and GekkoFS seems to work a little bit better when larger I/O sizes are used. At this point, I want to emphasize that for GekkoFS, the sequential I/O throughput on a file per process, or if GekkoFS would work on one giant file with all processes working on that file, is conceptually also indifferent because in how the way we are using it chunks in the backend. So the performance of file per process and a big shared file is actually the same. Similarly, if a large I/O size is used and it is bigger than the chunk size, then sequential throughput and random throughput also looks the same. Of course, if the I/O sizes are smaller than the chunk sizes, then we start to see the random I/O also happening on the chunks in the backend, which then degrades the performance a little bit. So to wrap this talk up, the file system is now finally available at this link, and you're very welcome to try it. GekkoFS will be used in the future as a basis for other EU projects as well. And as mentioned earlier, we will submit to the next IO 510 node challenge next month, so keep an eye out for that. In addition, we will continue to work on performance analyses on various applications to understand which configurations are beneficial to have in a file system. And eventually we want to modularize GekkoFS in a way to make it easier to tune the file system to applications. Finally, we plan to integrate the file system with data-aware scheduling. You can contact us at these mail addresses if you have any questions or feedback. And I'd like to thank you, and now I'm happy to take some questions.